If you go to the early universe right after the Big Bang, it was expanding way faster than the speed of light. Just like how CERN presented the heliocentric model, we may be in for another mind-blowing revision to our cosmic understanding. A debate has arisen in cosmology known as the crisis of cosmology. Neil deGrasse Tyson has said that the James Webb findings have ended this debate in a physics-shattering image. So, what exactly is this crisis, and how has the James Webb Space Telescope contributed to it? For some, it's hard to call it a crisis. It is a crisis, but for some old-timers, it's really hard. There was a time when we didn't know the age or size of the universe because they are related within a factor of 2. Join us as we venture into the very frontier of science, where our knowledge is constantly put into question and where we're making unanticipated discoveries. Over the past century, a significant achievement in cosmology has been the establishment of a standard model outlining the universe's history and its current state. Gravity, guided by general relativity, primarily dictates the universe's evolution, explaining both its expansion and the formation of large cosmic structures. The known components include dark energy, dark matter, normal matter, neutrinos, and photons. The universe originated from the hot Big Bang around 13.8 billion years ago, preceded by cosmic inflation, which caused density imperfections. But what if we told you that this very model is now under scrutiny? This model has been responsible for our understanding of the universe for the past century or so. Despite extensive observational support, this model might be incomplete. While we're getting more and more observations, each new one has to be examined in the context of the model to see if it still holds up. But astronomers have gotten a new tool in their toolset with the JWST, and this device has been creating problems for our standard model. It all started in the early universe before stars or galaxies emerged, when neutral atoms were forming around 380,000 years post-Big Bang. Then, 550 million years later, reionization occurred, ionizing most of the universe. The initial waves of reionization started approximately 200 million years after the Big Bang, with some stars possibly forming 50 to 100 million years after. The JWST, with its capabilities, allows astronomers to unveil more distant galaxies than previously possible, offering new insights into the early universe. First, let's go through what we know. The standard model of cosmology, known as the inflationary hot Big Bang or lambda CDM, has been remarkably successful. It explains various features of the universe, including gravitational lensing, the cosmic web structure and growth, the internal motions of galaxies, their relative movements within groups and clusters, and features in the cosmic microwave background. This model predicts that as we look further back in time and cosmic distances increase, the observed galaxies should be inherently smaller, bluer, less developed, and less rich in heavy elements. At some point beyond our current observational reach, we anticipate entering the universe's dark ages, devoid of visible stars or galaxies. But while verifying the integrity of these explanations, scientists have found conflicting evidence, resulting in a crisis of cosmology. The cosmology crisis is simple: we don't really know the age of the universe. Different methods give different results, and it's up to cosmologists to find out why, but they're struggling to do so. Let's take a look at the methods we use to measure the universe's age. The first one is cosmic background radiation. To unravel this cosmic mystery, scientists delve into the universe's expansion history, and to do that, they need mathematical modeling. This modeling is based on Einstein's general relativity theory. Applying this theory to the entire universe produces the Friedmann equations, linking the universe's composition, dark matter, dark energy, radiation, and more with its expansion rate at specific times. By measuring these contents, we can get the age of the universe using the cosmic microwave background CMB to do just that. The CMB is the remaining light from the early days of the universe when it was about 380,000 years old. It is a crucial tool in measuring the universe's contents. Exceptionally detailed maps of the CMB provide insights into the universe's composition. One such map is from the European Space Agency's Planck mission. But there's an issue with these maps: they lack data on dark energy, which is a significant player in the current universe. Dark energy didn't influence the early universe, so scientists must incorporate its effects manually based on other observations. Despite this, scientists can use the Friedmann equations to figure out the expansion rate of the universe at any point in time. They can even figure out the expansion rate today, and through that, determine the age of the universe. Another way to measure the age of the universe is by looking at exploding stars. While the CMB provides a thorough record of the universe's makeup, it's a historical snapshot originating billions of years ago. Another way to measure the universe's expansion is by directly observing its rate of growth. Thanks to Type Ia supernovae, a celestial spectacle where a star dumps its atmosphere onto a nearby white dwarf, the remnants of a deceased star. When the white dwarf hits a critical mass, it erupts into a supernova. Since this cosmic drama unfolds similarly across the universe, scientists consider supernovae consistent benchmarks or standard candles. This means we know their expected brightness, and by comparing it to their observed brightness, we can estimate the universe's expansion rate at the time of the supernova. This method, employed in the late 1990s, played a pivotal role in discovering dark energy, becoming a cornerstone in cosmological measurements. The JWST has complicated things further. According to deGrasse Tyson, the JWST has found things that, to our current understanding of the universe, shouldn't exist. Something had to change. Our current scientific understanding needs to be reworked, but we simply have no idea where to start. For instance, the JWST's recent images reveal galaxies much more distant and consequently older than anticipated by the standard cosmological model. This is yet another piece of evidence suggesting that our model needs updating. Hubble's groundbreaking revelation of the expanding universe relied on galaxies, and the JWST's images showcasing galaxies forming much earlier than current cosmological models predict have sparked a crisis in the field. So, how do we explain such a discrepancy? One solution proposes flaws in our CMB measurements, yet the Planck CMB measurements, among the most precise in science, have undergone extensive testing since their 2013 release, validating their accuracy. An alternative perspective suggests a potential gap in our understanding of dark energy. Perhaps dark energy varies over time, intertwines with dark matter, or involves another unknown factor. This possibility captivates theorists, sparking numerous exploratory papers. Lastly, the accuracy of supernova measurements could be questioned. Although more directly gauging the present expansion rate, supernova observations are not foolproof due to the complexity of exploding stars. If we don't completely comprehend the intricate physics, supernovae can't serve as a precise cosmological tool. A touch of uncertainty in supernova modeling could resolve the entire discrepancy. In conclusion, the crisis of cosmology remains, leaving scientists puzzled. However, the JWST's discoveries may be the key to unlocking the mysteries of the universe's age, composition, and ultimate fate. An emerging black hole emits ultraviolet radiation into the universe, stripping electrons from hydrogen atoms and enhancing transparency to UV radiation. After successive stellar generations, heavy elements and UV radiation become sufficient, allowing for galaxies to form. Gas quantities and stars collapse into gravitationally bound entities, uniting to form the first galaxies. While observational evidence supports key aspects of this narrative, challenges arise when integrating it into the cosmological framework of the expanding universe. The standard cosmological model establishes a link between observed distances expressed through redshift and the age relative to the Big Bang expressed in years. Distances are directly observed and are unchangeable values, while age emerges from theoretical constructs melding models of an expanding universe, guided by Einstein's general relativity and our comprehension of matter from the standard model of particle physics. Together, they explain how distance or redshift correlates with age, the duration since the Big Bang. The issue arose when the James Webb Space Telescope started operating. As soon as it started looking at distant galaxies, it found things that betrayed our current knowledge. It found galaxies much more distant and older than predicted by the standard model. The Hubble telescope had already hinted at this, but the JWST confirmed it. While the universe originated from the Big Bang, indicating its beginning, discrepancies emerge in the apparent age of the first galaxies compared to the age-redshift relations predictions. These galaxies seem to appear too early, which is impossible according to our current understanding. The foundational Big Bang model, depicting an evolving universe rather than a static, unchanging one, remains unchallenged, but there might be a need to update our understanding. Increasing evidence in the form of data keeps making us question this story. But how much needs to be changed, and what are scientists doing to get to the bottom of this? Scientists are turning towards even better equipment to answer these complex puzzles. One such venture is a project known as Flamingo. The Flamingo project, part of the Virgo consortium, engages in extensive computer simulations spanning from the Big Bang to the present to explore the universe's evolution. This program investigates the elements of the cosmos. Funding for this project was secured from the European Research Council, the UK's Science and Technology Facilities Council, the Netherlands Organization for Scientific Research, and the Swiss National Science Foundation. Throughout the simulations, detailed virtual galaxies and galaxy clusters emerge. Telescopes like the Euclid Space Telescope and NASA's James Webb Space Telescope gather data on celestial entities. The simulations will be compared to the observed data, letting us know how accurate the standard cosmological model is and if it really explains the universe's evolution to a good extent. Professor Carlos Frank, a collaborator in the Flamingo Research and Ogden Professor of Fundamental Physics at Durham University, notes a pivotal moment in cosmology. He says that cosmology is at a crossroads. New telescopes are very accurate, and the information we get from them doesn't align perfectly with our theoretical models, which in turn raises questions about the validity of these models or potential biases. The precise simulations aim to discern whether these discrepancies challenge the existing cosmological framework. Previous simulations primarily focused on cold dark matter. However, astronomers now emphasize the inclusion of ordinary matter, constituting only 16% of the universe, and neutrinos when comprehending the universe's evolution. Neutrinos are minuscule, infrequently interacting particles. Led by Professor Jup Shea from Leiden University, researchers conducted extensive simulations to investigate the universe's evolution.